This is CPE 133. This is Chapter 10 in the Free Range Verilog Foundation Modeling text. What we're going to be talking about is ripple carry adders, and then get into a little bit deeper into signed numbers and as they apply to ripple carry adders. The disclaimer: look, it's Verilog. The only way you're going to learn it is to do it. You're not going to learn it by watching boring videos or reading verbose text. So just break down and do it. You won't regret it. So this is about ripple carry adders. It's conceptually a simple circuit, but the implementations can get kind of complex. But once again, Verilog handles most of that for us, and we are going to bump this up to a high level as well. But this is the classic lower level definition here. Typically speaking, we have a bunch of 1-bit adders here, which are full adders, and then oftentimes we'll place a half adder in the least significant bit position. So the leftmost bit is the most significant bit here, rightmost bit is the least significant bit. Now if I use the half adder in here, it doesn't have a carry in, and so typically when I'm modeling ripple carry adders, I need a carry in. So generally speaking, this half adder, we don't put it in there. We usually put a full adder in there. Like I said, it gives the ability to have that carry in. So ripple carry adder, essentially, the carry ripples through this thing. Very simple device, not known to be fast because it takes a while for that carry to ripple through the thing. But this is our typical n-bit model here. So it adds 2 n-bit numbers and it kicks out an n-bit result, and also kicks out a status bit, which is the carry out. And typically we do various interesting things with that carry out bit. Verilog has a bunch of arithmetic operators. What we're interested in here for ripple carry adders is the plus, and also kind of sort of the minus. So this is our plus operator, and we'll be talking about the minus operator as well. So yeah, most times you see this in expressions. Oftentimes you see them in conditional statements as well. When you're using mathematical operators, it's really easy to think, wow, this is great. It's just like higher level programming, like a computer, but it's not. Essentially, it's completely different. So when I do an addition operation in a computer, it kind of knows that there's going to be the hardware in place that allows you to do that addition. Now, with Verilog, it's a little bit different. Now, when I use a plus operator, addition operator, for example, that means it's a message from me, the modeler, to the synthesizer to say, hey, give me the hardware that implements that addition. Okay, if I didn't put a plus in there, it wouldn't give me that hardware. So the act of putting that plus in there actually is going to make the hardware a little bit more complicated, because the synthesizer is going to do its very best to accommodate that request. In this context, the request is put a plus operator in there. The other issue here is we're going to typically be working with signed and unsigned numbers. It's actually quite confusing, so what we try to do is, I don't know, keep everything unsigned. Now, people argue that. Some people say keep it signed, but there's just issues here. The important thing is you know what you're doing with hardware. So the big issue here is the hardware doesn't know what you're doing. It doesn't know about signed or unsigned numbers. All it knows about is you're asking the hardware to add 2 numbers. It just cannot have any concept whether it's signed or not, or unsigned. So that's really important to realize. A lot of once again, it feels kind of comfortable working with these, but a lot of the work essentially left to the modelers to get the right result. Now, essentially, the issue is just, there's not that many rules, but you got to know them. Oftentimes, we can get away without knowing them, and then it catches up with us. But if there's not that many, I hope that you actually know these rules. The signed numbers are represented in two's complement notation, super popular notation. In my mind, it seemed kind of confusing, but I think after all the time I've worked with it, it just makes the hardware implementations a little bit more easy. easy to, and less complex, we'll say. That's the only reason I can figure out why everyone uses it, and I think it's a good reason. So the issue here, another issue is like adders and subtractors. We're talking about ripple carry adders, of course, but you know, does that mean I need a ripple carry subtractor or something like that? And I don't know. I mean, essentially, when I'm using addition operations and subtraction operations as part of Verilog, I don't really know whether the hardware generates a subtractor for me or not. My guess that it probably doesn't, because it takes advantage of the fact that a B minus C is equivalent to B plus a minus C, and using 2's complement notation, creating a minus C from a C is very straightforward. Essentially, changing the sign of a value using 2's complementation is very straightforward. These are some of the rules to follow here. Now they're not that complicated, but you know, when your hardware isn't synthesizing correctly, you're gonna have to understand this. You're gonna have to go back and look at these rules. So here they are. So the synthesizer looks at the expression. That means both the left hand and right hand side here, and it expands the width of all the operands in that expression to be the size of the largest operand in that expression. So if it's hard to say in one mouthful, but essentially the operands have data widths. What's going to happen is it's going to expand all the operands to have the same data width as the data width of the largest operand. Okay, I don't know if that helped or not. So the second rule here is that you, the designer, you got to know the appropriate bit width of your result. Verilog isn't magically going to do it for you. The example is if I add two 10-bit numbers, well, it could have 11-bit result, and I need to account for that. And essentially, my result needs to be 11 bits, or whatever I do with it needs to be correct. It needs to account for the fact that operands grow as a result of applying the operators. So when I'm expanding things, this is related to rule 1. When I'm expanding things, it expands things based on the signedness of the numbers. So if the numbers were declared sign, it sign extends them. If the numbers were not declared sign, it 0 extends them. Okay, so if not declared sign, it defaults to unsigned, of course. Yeah, simple, very simple rule there. And the last one is just every operand on the right-hand side of an expression needs to be signed in order for the result to be signed. So that means the ramifications of this are really important. If I have an expression with 10 operands on the right side of the equal sign, and one of them is unsigned, that means it will consider all those operands unsigned. All the operands on the right-hand side of the assignment operator will be considered unsigned. In that they're unsigned, they will all be 0 extended. So essentially, the presence of one unsigned operator will override all the signedness of all the other operators on the right-hand side of that equation. So it's very, very tricky, something you're not going to run into too often. We'll comment a little bit more about this in the next video, but these are the rules. They're not that complicated. Not that many of them. They are a little bit tricky. So this is our first example problem where we want to design this n-bit ripple carry adder. So it's n-bit. It's going to be a generic model. The issue with this is it is a generic model, so you can see the use of a parameter right here, but that's really not the important part of this thing. Now the important part of this thing is the cleverness of this particular model. Now you just have to, you'll see some examples later and it will bring you an appreciation of this cleverness, but let's just look at this thing. So everything in there, and this works. This actually works really good. Everything in here is declared unsigned, so which is fine. And so what happens is this is these are n-bit values here. This is a 1-bit value. So before it executes this operation, it expands C in to 4 bits. Essentially, well, we're assuming n we'll make it n equals 8. So n equals 8. So these are 8-bit values, and this is a 1-bit value, but it gets expanded to 8 bits. Because it's unsigned, it gets expanded using a 0 extension. So looking at the result here, there's 2 bits in the result. There's an n-bit result, and there's a carryout. It looks like, and they're concatenated together. Now, it looks like that could be like an n plus 1, like a 9-bit value, but it's not. It considers sum to be the largest value. So the largest value in this whole expression is 8 bits. So that's how it gets expanded. And so what happens here is it does this math, does the expansion, and it assigns these values in this format, which means the sum is going to be the lower 8 bits, and the carryout is actually going to be the carryout generated from this expression. Look, it works good as an adder. It always does the exact right thing. Don't have to worry about it. The question is when I'm using this for signed math, like some of these values are signed or not, I know I have them declared as unsigned, but they may come in as signed, but like from another module. I may be considering them signed in the hardware. So what happens is it's going to do this addition, and it's going to do it correctly. But once I start dealing with signed numbers, I have the notion that the result is it's always correct, but it may not be valid. Okay, and so what happens is, maybe hopefully remember it from your digital design course, is that to check the validity of that answer, typically I also use the carryout. Now, so this math here is always right for unsigned numbers, and it's always valid for unsigned numbers, but the same math may be incorrect when I'm working with signed numbers. I mean, the math is correct, but the answer may not be valid. The sum and the carryout may not be valid. I'm sorry, the sum may not be valid. Carryout's another issue. So those are all the issues with a ripple carryout. I know that's kind of a lot, but it's usually not too complicated once you start working with it. So the next thing we're going to do here is there are some underlying issues when working with signed and unsigned numbers, and we're going to look at some problem cases in the next video.